Or in other words, towards the source side, you have more electrons. But those electrons move slowly. And then towards the drain side, you have less electrons, but those electrons move very fast. So we consider those two facts, right? Electron move slowly, and then towards the drain side, electron move less electron, but they move fast. So the product of those two factors determines your current, which is continuous. Okay, so this is the current we have seen before, and we will define this VGS minus VT as gate overdrive, or we give a name like VOV. Because later we are going to compare this VOV with your drain voltage VDS to determine the linear region or the saturation region. So if we plot this ID versus VD in this ID-VD curve, it will be something like this. Okay. ID versus VD. If you just use this formula and draw the curve, it will be a parabolic function because this is second order term with the VDS. So that must have a peak, and then it will be something like this. That means here the turning point is this VGS minus VT VOV. So this is not true, right? Because as the drain voltage increase, current should not decrease. So this part is not true. This is where we enter the saturation region. So we cannot use that equation anymore once we reach here. So this is when the VGS minus VT equals to VDS. So at this moment, we said that the pinch-off happened. Pinch-off means the electron density of the channel towards the drain side here reduced to 0. Then we cannot use the previous assumptions anymore. So this is the pinch-off condition, and all the electrons here will be swept to the drain immediately because we don't have more electrons to supply this current. Then the current will be saturated. So this is the first order assumption. The channel will be pinched off, and then the current will become a constant. That is the saturation current. So if you use that assumption here, then you have a flat line here. That is the saturation region. This is what we have seen before, the ID versus the VDS. And then if we plug in this condition, when the VDS equals to VGS minus VT, then you can get this VDS. You plug in the VDS equals VGS minus VT, then you will get the saturation current, which is the square law. It's half mu COX W over L, and VGS minus VT squared. That is this current. And we also have seen this kind of ID versus VGS curve, right? So this is ID versus VGS. And then here we have the threshold current, threshold voltage. And above that, then you have the saturation region here and the linear region here. So this is the trial region and the saturation region. And here, as we discussed, if the VDS is very small, so you can ignore the second order term. If you ignore the second order term here, that means you are going to take the slope of this one. So the current is proportional to the drain voltage. That means it's like a resistor. So the channel resistance of the transistor is a slope here, 1 over the slope, 1 over of the slope. Conductance will be the slope, and this is the current versus voltage. So let's say conductance is the slope, and resistance is 1 over this slope. So if you do that, you will get this slope as mu n COX W over L, and then this VOV, which is VGS minus VT. So in this case, you can think the transistor is like a resistor. So in other words, we think this transistor is almost like a resistor. And this resistance is given by this equation. So any questions? So here, we still mostly review what we have discussed before.
So we use the channel resistance to approximate all the way up to the end of the triode region, even when it starts to be a curve?
That's not a good approximation. I would say at the very beginning of this triode region. Yeah.
It's only while it's still in here?
Yes, yes.
Okay.
So somewhere here.
Okay. Is there like a cutoff or something we're going to look at for that?
There's no hard boundary, right? Just depends on how accurate you want to be.
Okay.
So I would suggest maybe the VDS below like 100 millivolts, then you can use that. Okay, so this is the equations and the two curves we have seen before. And then we can also have the summary table like this, or chart like this. So depending on the gate voltage and then the drain voltage, you have those three operation regions. So first of all, the gate voltage below the threshold. This is the subthreshold region, which we have talked about in the previous section. And when the VGS is larger than the threshold, then we need to look at this one, this VOV. VGS minus VT. This is VOV, the gate overdrive. So we need to compare this VOV with the drain voltage. So if the drain voltage is larger than this VOV, then we are in this saturation region. When the drain voltage is smaller, then we are in this triode region. So in the triode region, we just said that if the VDS is very small, we can ignore the second order term here. And we can ignore the second order term here. We can ignore this term. So if we ignore this term, then the current is proportional to the drain voltage. That's why we said you can approximate the transistor as a resistor. And this resistance of this resistor is just this basically in front of this VDS, you have this conductance. This whole term is the conductance. And then the resistance will be 1 over this conductance. That is 1 over this term. So that is the resistance of this resistor. If you approximate the transistor as a resistor when the VDS is very small. On the other side, if the transistor is in the saturation, so the drain current is independent of the drain voltage, because here, let's say this is source, you ground, this is a drain. So you have VDS across that. So here also you have the source and the drain, and you have VDS across that. But if you look at this equation has no VDS in the saturation equation, right? There's no VDS. No VDS, that means the current is independent of the drain voltage. If the current is independent of the voltage, so what circuit element is it? If current is independent of the voltage, you have a constant current. That means it's a current source, right? Regardless of your load, your current is a fixed current. That means no matter what is your drain voltage here, we provide a constant current. So then this is like a current source. But here we say it's a voltage controlled current source. VCCS is voltage controlled current source. This voltage control is what voltage? It's a gate voltage control. VG. Because you have another terminal, which is a gate here. If you tune the gate voltage, you are going to tune the current level. So it's like the gate-controlled current source. It's independent of the drain voltage, but it's controlled by the gate voltage. Any questions? All right, so let's look at some of the parameters used in those equations. So here, this is a saturation current. We also call it the square law because you have the square term here. And let's look at some of the notations. You may see that in the new textbook, the Cedar Smith. So sometimes we represent the mu COX as this Kn prime. Mu and COX as a Kn prime, just for notation. And then if we also consider the geometry parameters W over L, the width over the length, then we can get this, define this as a Kn. So if you do that, then you can simplify the formula like this. It's just a notation. And let's look at the units. First of all, this COX is a gate capacitance of that MOS structure. You have oxide. So that oxide will give you the capacitance. And this is a unit capacitance. That means the capacitance is normalized to the unit area. So this capacitance is this unit capacitance COX is given by epsilon oxide divided by the TOX. So that is a dielectric constant of the oxide. Of course, if you want to make it more rigorous, you should have the, let's say, the permittivity of the vacuum. So basically, the permittivity of the vacuum multiplied by the relative permittivity of the oxide divided by the thickness of that oxide. So the unit will be this Faraday over, let's say, centimeter square, because it's a capacitance as a unit far, and then divided by the unit area, centimeter square. We always use centimeter here for the distance, for the length. And then mu is the mobility. We have seen this before. And the unit of the mobility will be the centimeter square divided by volts. This is for voltage, volts. And then S is a second. That is for time. So this is the volt. This is the second. And then the Kn prime, you are going to use this mu times the COX. So if you do that, these two units, let's just do the multiplication of those two units. So the centimeter square will be cancelled. So what is left is this bar over volt times the second. And if you do the conversion, it's the same as ampere per volt square. So ampere is the unit for the current. And then if you further multiply the W over L, still is this unit. Because W over L will be unitless. So W and L both are distance. Then they cancel each other. So you still have this one. So Kn has this kind of unit, but then later you are going to multiply by the voltage squared. Then that means this will give you volt squared. Then this volt squared will cancel this mode squared in the denominator, so eventually you get the ampere for the current. Okay, so the question here, if you look at this equation, the question is, can you change those parameters? If you design the transistor, can you change? So depending on the role or your job, so depending on you are like a circuit designer or you are a device engineer, so then the tuning knob will be different. So if you are a circuit designer, for example, for those design house or fabless companies like let's say Apple or Qualcomm, so you cannot change the technology parameters. So what you can change as a circuit designer, you can change the geometry, you can design the structure of your transistor. Mostly you can change the W, how wide your transistor is. If you want larger current, of course you will design it wider, larger W, because it's proportional here, you see. And then the L, you can also change that, but depending on the technology load. So you cannot change the L below the minimal technology, minimal L provided by that technology node. For example, if your technology node is 65 nanometer, then you can design your L above 65, but you cannot do that below 65 because that is a minimal L limited by the lithography constraint of that node. And then you can always change the voltage, like VGS minus VT, especially the VGS. You can always change the VGS to change the current. Okay, so this is what you can do as a circuit designer. But if you are a device engineer, for example, if you work for like TSMC or like Samsung Foundry, they fabricate the transistors. Then you can design your like threshold voltage. For example, you have learned before, threshold voltage depends on the doping, right? The higher doping, the higher threshold voltage. So you can change those fabrication recipes to change the doping, and then you can change the threshold voltage. But you cannot do it if you are a circuit designer because you are not fabricating the devices. You just design the circuits. Then the device engineer can change the doping to change the VT. And the TOX and COX is almost fixed. And then the mu is what you get for that technology. It's very hard to change. So this is, of course, from one technology to another technology node, those parameters will change. But if you have the same technology node, then you cannot change the TOX or the mu. Okay, so this is about the parameters. Any questions? Then here is the example to practice the IV model. So the question is, if your L is for this technology node, then the L is like minimal L is 0.4 micrometer, QX is 8 nanometer, mu n is mobility of electron, 450, and threshold voltage 0.7. Then find the COX and the Km prime. So this is just practice the equations, and you can do it. And